Hi everyone, this is Aidan for Fluid Mechanics 101, and today I'm going to be talking to you about the k-epsilon turbulence model. So just to give you an overview of what I'm going to talk about today, I'm going to introduce the standard k-epsilon model. I'm then going to look at how has the model evolved over time and what variant are you using in your CFD codes today. I'm then going to go on to look at what are damping functions and why are they needed in the k-epsilon model. And finally, I'm briefly going to look at what are high Reynolds number and low Reynolds number variants of the k-epsilon model. I really think in today's talk you're going to find it useful, as I'm going to provide some deeper insights into the k-epsilon model which you may use in your day-to-day CFD career, and I really think you'll find this talk very useful. So just to start things off with a brief reminder of what the k-epsilon model's function is we're going to start with the Reynolds averaged Navier-Stokes equations, or the RANS equations, which you see there in equation 1. And just a reminder that in the RANS equations we have this additional term, the Reynolds stress on the right hand side, which arises from the Reynolds averaging process. And what the Reynolds stress is it's the product of the two fluctuating velocity components averaged and then taken the divergence of that term, and that gives us this additional Reynolds stress term, which is an unknown in our RANS equation. And so if we want to close the equations and solve for the mean velocity u, which you can see there, we need to have a model for the Reynolds stress, or more correctly, we need to express the Reynolds stress in terms of quantities that we know, so that we can solve equation 1 for the unknown, which is the mean velocity field u. And the most popular way of doing this is with the Boussinesq hypothesis, which you can see there in equation 2. And what we do with the Boussinesq hypothesis is we relate the Reynolds stress on the left hand side there to the mean velocity gradients in the flow, which are indicated there by the underbrace term. And the Reynolds stresses are related to the mean velocity gradients by the dynamic eddy viscosity or turbulent viscosity, which is given by mu subscript t there in equation 2. And so when we make the Boussinesq hypothesis there in equation 2, all we need to do is we need to be able to calculate what the eddy viscosity is, mu t. Once we know what mu t is, we have the mean velocity gradients, and we can use that to express the Reynolds stress term there in the RANS equations and close the system of equations. So what we're doing here, just a reminder with the RANS model, is we need some way of calculating the eddy viscosity mu t, and that's where the k-epsilon model comes in. So I'm going to start with a bit of history here, which will really help you to understand actually what the k-epsilon model is doing. Now, earlier RANS turbulence models, before the k-epsilon model, used a mixing length approach to calculate what the eddy viscosity is. And the mixing length is commonly denoted by L subscript m to mean mixing length. And what does the mixing length physically mean? Now, the mixing length physically represents an indicative size of the turbulent eddies that exist in the flow. Now, remember, of course, we're going to have a full spectrum of sizes and energies of the eddies, from the largest possible eddies in the flow all the way down to the smaller microscopic eddies in the flow. And the mixing length is really an indicative size of those eddies. So in an area of the flow where we have very large energy and eddies, the flow is very energetic and very turbulent, our mixing length is going to be very large. And what that then means is, following equation 3, either of those forms you commonly see in the literature, because the mixing length is large, that means our turbulent or eddy viscosity is going to be large, and we're going to get a lot of mixing in our RANS equations. So how do we specify this mixing length? Because this really is just an indicator of what the turbulent structure is like at that region in the flow. And one of the earlier approaches is the Prandtl mixing length hypothesis, which you can see there in equation 4. And what the Prandtl mixing length hypothesis says is that if we're at some distance y to a wall, then the maximum size of the eddies is limited by the presence of the wall. So if you look at the small sketch which I've provided there, when we're very close to the wall, the maximum size of the eddies that can exist between our position and the wall is very small, and as we move further away from the wall, we're permitted a larger size of eddies in the flow. And so Prandtl proposed a hypothesis there in equation 4 that says the mixing length is proportional to this distance y times by some scalar kappa, which happens to take a value of 0.41. So as we get closer to the presence of the wall physically blocks the size of the eddies. Now, of course, this isn't the only mechanism that's occurring near the wall. We also have the action of viscosity in the viscous sublayer very close to the wall. So an improvement on the Prandtl hypothesis is the Van Drießt mixing model, which says as we approach the wall, the action of viscosity is also going to dampen those eddies, and a way of interpreting this is reducing the effective size of the eddies in the mixing length hypothesis. And so if we reduce the mixing length, we're also going to reduce the eddy or turbulent viscosity there, which is reducing the mixing in the flow due to turbulence. And this is what we expect as we approach the wall. And the Van Drießt model takes the form there given in equation 5. You've got kappa and y at the front multiplied by some exponential decay. And you can see from the plot there, the dashed line being the original Prandtl model, which is just linear. As we move away from the wall, the mixing length gets larger. But then the solid line there shows that when we account for the viscosity in the viscous sublayer, as we approach the wall, the mixing length is smaller than we expect from the Prandtl model. And this really forms the basis of early RANS turbulence models. And the reason I've introduced this, you'll see later, because it also motivates some of the decisions in the standard k-epsilon model. And we'll return to this a bit later. So what you'll have noticed from these early eddy viscosity models is that the mixing length is specified algebraically. And what that means is that the mixing length only depends on the distance to the nearest wall. And what that means is that if we have our given geometry, then the distance to the nearest wall is specified throughout the entire domain. And this is fixed unless our geometry is moving. The distance to the nearest wall is fixed, so the mixing length is fixed, and therefore so is our eddy viscosity there. However, we'd like to make some improvement on this model, and the reason we'd like to do this is, as we know, turbulence is convected and diffuses through the flow. It isn't static and fixed at some distance from the wall. And so what we'd like to do is we'd like to solve a transport equation for our turbulence quantities. And the way that we do this is we can solve a transport equation for the turbulent kinetic energy K, and we'd also now going to solve a transport equation for the turbulence dissipation rate epsilon. And if we do that, we solve a transport equation for K and a transport equation for epsilon, then we can use equation 7 there to give us the eddy viscosity mu t, and then put that back into our RANS equations, and that allows us to close the system and solve the system of equations. Now, the key point to note here is that if we take equation 7 and equation 6 and combine them, what we see is that the mixing length, L sub m, is actually directly related to the dissipation rate epsilon. So when you're solving your transport equations in the k-epsilon model, the transport equation for K obviously represents the turbulent kinetic energy in the flow, or the energy and the strength of the mixing, but the equation for epsilon, even though it's termed the dissipation rate, is really another way of solving a transport equation for the mixing length, or the physical size of those eddies. So often you may see the equation for epsilon referred to as the dissipation rate equation, or as a scale determining equation in the k-epsilon model. So now let's go ahead and look at the equations in a bit more detail. What are the transport equations? Now, the transport equation for the turbulent kinetic energy K takes the same form in the RNG, realizable, and standard k-epsilon models. And the equation is given there in equation 9. On the left-hand side, as normal for transport equations, we have a time derivative, a convection of turbulent kinetic energy, And then on the right hand side we have a diffusion of turbulent kinetic energy and sources and sinks of turbulent kinetic energy there. And the sources of turbulent kinetic energy can be due to mean velocity shear, that's pk, production due to buoyancy, and we may also have some user-defined sinks there, sk. And note also that we have a negative there, which includes the dissipation rate there in the transport equation for turbulent kinetic energy. And this is showing us that the equation for epsilon is actually acting to dissipate turbulent kinetic energy in the flow. Now this transport equation is the same for the RNG, realizable and standard k-epsilon models, so it doesn't matter which form of the equation you're selecting, you're always going to be solving the same transport equation for k. Now the difference in these three models is the dissipation rate equation, as I'll show you in the next slide. And I'm going to be focusing on the standard k-epsilon model as it's the most popular, but the RNG and the realizable follow directly from this with small variations in the equation. Now the transport equation for epsilon is very similar. Again, we have a time derivative, a convection term on the left hand side and a diffusion term on the right hand side. Then we also have sources and sink terms there, which are indicated by the underbrace. But what you'll also notice here with the sources and sinks is that we've got some empirical model coefficients, C1, C2 and C3. Now these empirical model coefficients will vary depending on the variant of the k-epsilon model that you choose. They'll vary between standard, RNG and realizable, and they'll also vary between which variant of each of those models that you choose. And that's what I'm really going to focus on today. Now, of course, just a reminder here that once we've solved these transport equations for k and epsilon, then we use equation 11 to calculate the eddy viscosity, put that back into the Boussinesq hypothesis and the Rans equations, and we can close the system. So what are the model coefficients? Well, it turns out that the model coefficients have actually evolved through time, even in the standard k-epsilon model. And if you actually look into the user manuals for your CFD code, you should be able to pick out which versions of the model coefficients are being used by your solver. And what I've listed here are three of the earliest papers which document the k-epsilon model, starting with the original paper by Jones and Launder in 1972, and then two updates on that paper in 1974. What you'll see from the table is that the model coefficients C1 and C2 have been updated. So if you were to compare your user guide with the original paper for the k-epsilon model, you may think, why are the coefficients different? Well, it turns out that actually modern CFD codes use the updated form of the coefficients, which are highlighted in red there, because they've been shown to give much better performance. So hopefully if you're looking at model coefficients, that should help clear things up as to which version you're using. And also for those of you who are interested, you can also go ahead and dig out those papers, which I've put links to in the description below the video, and I'll show references at the end of the slide. So if you want to have a read, those papers are available and you can look at them in more detail. Now, we're going to have a look at a little bit at damping functions. If we remember back to the mixing length model that I introduced at the start of the paper, the mixing length was damped close to the wall, and the reason for this was to account for the action of viscosity in the viscous sublayer, which is reducing the effective size of the eddies or the strength of the dissipation that they introduced. Now, remember in the k-epsilon model, we're not solving for the mixing length, we're solving for the dissipation rate epsilon, sort of in place of the mixing length. And so we have to have some way of damping the dissipation rate close to the wall, as we don't have a mixing length now. And the way we do that is specific damping functions are applied to those model coefficients C1, C2 and C mu. And what you'll see if you look at the damping functions, they're termed F1, F2 and F mu, and the subscripts directly correspond with the coefficients that they're damping. So what that means is that the damping function F1 damps the coefficient C1, the damping function F2 damps the coefficient C2, and so on. And by applying these damping functions, what it means is that in theory we could apply the k-epsilon model all the way up to the wall, or what that means in a CFD code is we can solve the equations even when our cell that's closest to the wall is in the viscous sublayer. And this formulation of a k-epsilon model is called the low Reynolds number formulation. So whenever you see low Reynolds number formulation of the k-epsilon model, that means that some empirical damping functions are being used in that wall, in close to the wall, to reduce the dissipation rate close to the wall. And don't worry, I'm going to dive in and look at these damping functions in a bit more detail, but I should first point out that there are a wide variety of damping functions that are in use in CFD codes at the moment, and I'm really just going to focus on the original damping functions for the standard k-epsilon model so that you can understand and see where they're coming from. So what are the damping functions in the standard k-epsilon model? Well, we have F1, F2 and F mu there, given in equations 13, 14 and 15. And what you'll notice is that the key parameter in these damping functions is the turbulent Reynolds number. So that's Re with a subscript T for turbulence. And this may not be a quantity that you've necessarily seen before, so don't worry, I'm going to take a bit of time to explain what this parameter is and where it comes from. And then using that, look at the damping functions in a bit more detail. So when we think of Reynolds number, what we usually think of is a ratio of some inertial forces to some kind of viscous forces. And then usually the Reynolds number takes some kind of approximate form as given there in equation 17, with a density, a velocity and a length scale divided by a viscosity. And if we're thinking of a Reynolds number that characterizes the strength of the velocity fluctuations and the turbulence near the wall, then the form of that turbulence Reynolds number is going to be the density and then multiplied by the square root of the turbulent kinetic energy, because that represents the effective strength of the velocity fluctuations near the wall, and then the length is going to be the mixing length and then divided by the dynamic viscosity there near the wall. Now remember from before, we're not solving for the mixing length in these models, we're solving for the dissipation rate. So if we substitute in for the mixing length there in equation 18, we arrive at equation 19 for the turbulent Reynolds number. And what does the turbulent Reynolds number mean, and what do we expect it to take? Well, near the wall, our turbulent kinetic energy K is going to be reduced, it's going to be small, and we expect our dissipation rate to be very high. So what that means is that the turbulent Reynolds number is going to be small. So a small value of turbulent Reynolds number is indicating that viscous forces are dominating, whereas a large value of the turbulent Reynolds number indicates that turbulent forces are dominating and implies that we are further away from the wall. And that's the key aspect that's going to be used by the damping functions. So if we go back to F mu, this is the damping function that's applied directly to the eddy viscosity. We see there in equation 20 that F mu is multiplied directly to C mu, and the form of the damping function given there in the original paper is in equation 21. Now we can take the two extremes and we see that far away from the wall, when the turbulent Reynolds number tends to a large number or tends to infinity, then F mu is going to tend to 1. And that's what we expect. Equation 20 will return to the original form that we introduced earlier in the paper. However, if the turbulent Reynolds number is very small, that would indicate that viscous effects are large and we're very close to the wall, and we're going to be reducing the value of the eddy viscosity. So what does that physically mean? Remember, we're close to the wall here and we're expecting the effect of molecular viscosity to dominate turbulent viscosity. And so as mu t is getting very small, that means in comparison the laminar viscosity is going to dominate the diffusion term there, which you see in equation 2. So the damping function F mu does provide the behavior that we would expect. And just a small reminder for you here about what the damping function actually is. As with all of the equations we've introduced in this slide set, remember that the damping function is actually a field. It's not a single value. So it's not going to take a value of 1 or a value of 0.8. There's going to be a different value of the damping function in every cell in the mesh. And I've given you just an example sketch here to indicate what this might be like. And far away from the wall, you can see that this damping function is bright red and it's going to have a value of 1. But then as we approach a wall, the turbulent Reynolds number is going to get very small, and our damping function is going to take a value much less than 1. And so if we were to calculate and plot this field, what we could deduce is that values where f mu is equal to 1, we're using a high Reynolds number formulation of the k-epsilon model, but in locations where f mu is much less than 1, that would indicate that we're using a low Reynolds number formulation of the damping function. Now let's look at the other two damping functions. So the damping function f1 is applied to C1, the coefficient 1, which appears in the production term for the turbulence dissipation rate. And in the original paper, Launder and Jones investigated different values of this damping function f1 and didn't find any noticeable improvement. So they just left the damping function as 1. What about the other damping function f2? Now, f2, once again, is the damping function that's applied to the coefficient C2, which happens to appear here in the dissipation term for the dissipation of turbulent kinetic energy. And so what this means is that F2 acts to reduce the dissipation of epsilon near the wall, and of course epsilon in turn dissipates turbulent kinetic energy. So what this means is that we're going to get more dissipation of turbulent kinetic energy near the wall, and this is the action that we expect from molecular viscosity to near the wall. So it may take a minute just to pass and think that through, but F2 does provide the expected behavior that we get near the wall. So that may have been quite a lot for you to take in, so I'm just going to provide a quick summary for you here. Now, in a low Reynolds number formulation of the k-epsilon model, damping functions are applied to the model coefficients C mu, C1 and C2. And the reason these damping functions were introduced is to give the user the option of being able to resolve the equations all the way down into the viscous sublayer, and the damping functions are effectively reducing the value of epsilon in a similar way to how the mixing length was reduced in earlier models near the wall. Now, it's very important that I plant a flag at this point and say that for your own CFD applications, if you are running simulations where you're interested in the flow very close to the wall, so if you're interested in accurate wall shear stress and heat transfer predictions, and you're trying to get y plus of less than 5 or less than 1, perhaps you're doing external aerodynamic simulations or turbomachinery simulations, it's very important to remember that while the k-epsilon model in its low Reynolds number form does have the capacity of resolving these flows, the k-omega SST model is widely accepted as providing better performance for these low Reynolds number applications. And the reason for that, remember, is that the k-epsilon model was originally introduced in the early 1970s, and the k-omega SST model was introduced much later, some 20 years later than the k-epsilon model. And after a thorough comparison in the literature, it's been widely established nowadays that for those low y plus flows, the k-omega SST model does provide superior performance. But nevertheless, the k-epsilon model is usually preferred for high Reynolds number applications. So if you're running simulations where your y plus is greater than 30, then you can use a high Reynolds number formulation of the k-epsilon model, which doesn't involve any of these damping functions, and the k-epsilon model is still a very popular model to use there. But hopefully now, if you dive into your user manuals or source code, you should understand a little bit better what these damping functions are and the different variations and where they're coming in. And of course, for those of you who'd like to go back and read the original papers for the k-epsilon model and where it was proposed, I've got the 3 main papers linked down in the description below, so you can quickly have a browse through those if you're interested. And that just about wraps up the talk from me today. I'd like to finish off by once again thanking all of you for your support for the channel. I really do appreciate it. Every comment and piece of feedback and suggestions really help me to produce more videos and really help keep my confidence going with this channel. And at this point, I'd also like to particularly thank my patrons over on Patreon for supporting the channel as well. And if you'd like to find a way where you can show your support for the channel, there are a number of ways you can do this. You can either buy me a coffee or a donation on PayPal, or you can even head over to my website, which is also linked down below, where you can find lecture notes for some of the other popular talks that I've given on this channel. And you could also support the channel through Patreon. And one of the benefits you get from supporting the channel through Patreon is access to the PDFs lecture slides for all of the lectures that I've put up onto YouTube. So perhaps if you want to look at those slides in your own time, print them off and study them, then head on over to Patreon and you can get access to those slides there. And once again, thank you all so much for supporting the channel, and I do try to answer all of your comments and suggestions down in the comment section below. So if you have any suggestions or thoughts or further questions, perhaps I've missed something out, then please just drop a comment below and I'll get to you as soon as I can. Thank you all very much for listening, and I'll see you next time.